So Graham's not here today, so I'll be talking about advanced search algorithms. We have already, how do I change that?
Oh, you just need to click on the quick ones on the PDF and then just do it.
Okay. So we have sort of seen beam search before in this class, but I'm going to be going into more detail in various ways of improving beam search and various other search algorithms. But even though we have already seen a little bit of beam search, most of the decoding we have done in the class so far has been greedy. You take a softmax, you pick out the best example, you assume that's correct, and you continue. And oftentimes we can do better than just greedy decoding. So this is the most basic one, I guess, and we have seen it before, so I'm going to move quickly. But with beam search, instead of picking the best example from your arg softmax, instead of picking the highest probability, you maintain multiple paths. So if you're doing beam search of size k, you maintain k paths. At each time step, you expand those, and then you choose the top k paths out of those and continue. And I'm not really sure if we're going to go with this example, but if, for example, you did have a situation like this, and you were going word by word, if your next word is Pittsburgh, the other next word for both New York and New Jersey is going to be new. And their combined probabilities here is going to be 5.5, which is higher than Pittsburgh. And then your next step, you're going to choose New York, because it's a higher probability than New Jersey. So you're going to choose New York here, even though it has a lower probability than Pittsburgh. So something like beam search can help over this. But we can go beyond just basic beam search. So for example, normally you just pick the top k highest scoring paths at each time step. And you can imagine doing other things. So you can pick at every path in your beam within a threshold of the best score. You can also do a prediction-based pruning method. So in their specific case, in Stern et al., they were doing constituent-based parsing, where that looks something like if it was he bought an apple, it'd be something like he bought. And they were doing this in a shift-reduce-based method, sort of similar to the ones we've seen before, where you shift words onto the stack and then you reduce them to form constituencies. But here, for instead of shift-reduce, it's called open and close, where open creates a new bracket, and then you assign it a part of speech tag, and close closes off a parentheses and creates a constituent. And there are opens equal to the number of possible tags in your data set, and there is only one close. So at any given time step, it is fairly likely that each open is going to have a smaller probability than the one close. So the probability mass is going to be spread out over the opens. So in order to balance these classes, what they did was they trained a simple feed-forward network to choose which actions to prune. So they trained this by, for each training example, whenever they called open, they had the gold label. So they fed in the action sequence to their feed-forward model, and they just had it predict which of the which of the open actions is the correct one, and they chose that one. So they applied this to their beam search in order to balance the action sizes, to make the number of opens closer to the number of closes. There are also backtracking-based pruning methods. This isn't quite beam search, because in this one paper, they were doing dependency parsing using a shift-reduce LSTM-based parser. And here, instead of doing just simple beam search, they rolled out to the very end of the beam. So you sample one entire sequence, and you store the midpoints of each sequence. And then you want to choose which of those midpoints is the most uncertain and explore from there. And that gives you a fairly good idea. Trying to decide which one's the most uncertain is perhaps we're making a mistake here. And they chose which one's the most uncertain by comparing the most probable action and the second most probable action of each state in the sequence. So you take the difference of those two. Whichever one has the smallest difference is the one that's the most uncertain about its first best action and its second best action. And they chose that one to roll back to. So you roll back to that state, and you continue to expand. I guess another potential question for beam search is what beam size should you use? Oftentimes, larger beams will pretty much always be slower, and they won't always give you better results. We'll talk about a bit more about later why. But one of the major problems is they tend to favor higher frequency words. And honestly, a lot of times the way to get the best beam size is just to experiment. Try a bunch of different beam values. 5, I've seen beam sizes go up to 100. It depends on how much computing power you have. Yeah. And another potential problem is oftentimes you're going to have variable length output sequences. And larger output sequences are on average going to have lower probability. So if you're doing, for example, machine translation, and your target output should actually be really long, each time you're generating a word, the probability of the sequence is going down. So you want to be able to normalize that. So different length output sequences have approximately equal values. So there's a very simple idea, just divide by the number of elements in the class. And this tends to work pretty well. If you're not particularly concerned about getting every last little point of blue score out of your model, you can probably just normalize the number of actual sequences and it will be fine. But if you want to try to do better, there are quite a few things you can do. Google's machine translation system did a peeping for normalizing it. Instead of normalizing by the output sequence, by the length of the output sequence, they normalized by 5 plus the length of the output sequence to a parameter, which was 0.6 or 0.7, and they divided that by 6 to the same parameter. And there was no theoretical justification for this. This was them being like, we're Google, we have 1,000 GPUs, let's just try every single possible value. So if you find yourself in a similar position where you have a lot of computing power, you can turn the normalization factor into a parameter and try to tune that. They also did a cool thing where the second term, the CP term, is a coverage vector. So in machine translation, oftentimes you're going to want more or less every single word in the input sequence to be covered by the output sequence. And what they're doing here is they're just doing a sum over the input sequence and a sum over the output sequence of the attentional weights. And they're taking the min of the attentional weights and 1. So this gets a higher penalty for each word that is not covered. And the idea for this is just trying to push the translation system in your search phase to cover every word in the input sentence. And they got pretty impressive results with this, although all of the parameters here they found empirically, and there's really not much of a theoretical justification for them. You can also predict the output length. What they did here was they calculated the probability of the target length given the input length using corpus statistics, and they trained a model for an input sentence to predict the output sentence. And then they penalized their system in search from differing from that predicted term. So if the probability of the output sentence was strong enough, they could override the predicted length. But if there were a few translations that were pretty close to each other, they would tend to favor the translations that were closer to the predicted length. And now we're back to, I guess, why bigger beams can actually hurt your performance. So in this paper, they ran experiments with progressively increasing beam sizes, and they found that increasing beam sizes always more or less decreases your model loss. So if that's all you're concerned about, you don't have an external evaluation factor, just use as large a beam as you have the computational resources for. It's going to help. But if you have an external reward, such as blue in machine translation, I think they use machine translation examples here, this will oftentimes lead to decreased score. And their theoretical reason behind that was they thought that the model was spreading its probability masses too evenly across all of the examples. And because of that, as you increase the beam size, you're going to see more and more marginal translations that have artificially high probabilities that the model is going to like and choose with beam search. And that's going to be what decreases the final score. So the justification for why it's spreading its probability too much was twofold. First of all, there was sort of an intrinsic thing. If you're doing machine translation, oftentimes there'll be multiple good translations. But there's also sort of an intrinsic uncertainty, which came from bad data preprocessing. They looked at WMT in specific, and they found that in the English and maybe German dataset, something like 1% of the sentences had the source sentence copied directly to the target sentence. And if you're feeding that into your model, that's adding quite a bit of noise, especially at the frequency they found it in. And that never is going to occur in test time. I don't think WMT for a competition is going to be like, I want you to directly copy the sentence in the test corpus. And because of this, that added quite a bit of uncertainty to the model and increased a bunch of marginal translations. For example, just copying the source sentence. And that meant whenever you were running larger and larger beam searches, it was considering these more and more marginal things that had artificially high probabilities that they should not have. So the combined impact of these both intrinsic and extrinsic factors made it so that expanding beam search effectively compounded this problem. And they proposed a couple of ways of mitigating it, but one of the biggest impact ones was just making sure your training data is good. If you're doing WMT or machine translation in general, one of the most common annotator errors is copying the source sentence. It might be like a copy-paste problem. And that's pretty easy to filter out, and they got fairly large improved accuracies with larger beam scores after they filtered out copied source sentences. I sort of mentioned this earlier, where you can have problems if you have disparate action sequences. And there were quite a few other ways of dealing with that beyond pruning. In this paper, the same one that was doing the constituency parsing, they were also working on generative constituency parsing. And in a generative model, instead of shifting the top word of the sentence, you have a generate function. And generate generates one word from your vocabulary. So instead of having one possible shift, you have generates equal to the size of your vocabulary. So where before these word tags, you would have 24 word tags, and training a pruning model is pretty reasonable. Now you have 10,000 shifts, and training a pruning model on that becomes a much harder task. You're essentially trying to predict the next word of the language model if you try to do that. So instead, they simply decided, instead of comparing beam search at each state equal to the number of actions. So normally you would compare beam search of, say, one translated word, two translated word, or in the case of shift-reduced parsing, you do the comparison with one action, two actions. Instead, they created buckets, and these buckets were buckets of equal numbers of shifts. So you're only comparing sequences of actions with equal numbers of shifts. And that creates a much more fair comparison, especially in uncertain cases where the next word, for example, if you predict the, there's a lot of possible nouns that can go with that. The probability masses can be very spread out. So in practice, what the model likes to do if you just throw a beam search at it is close every single possible word that can be closed before you're forced to pick the next action. So to get around that, you simply compare the probabilities of equal actions. So you produce the, and you do a comparison. You do any number of closes, and you produce the noun, and only then do you do a comparison. In practice, they did this by buckets. They had a bucket of I, which is the number of shifts, and then the number of other actions in the bucket. So then you have your bucket, and you predict the next action on that. And if the next action is shift, you shift that to the next bucket over, so it would be I plus 1. And if the next action is an open or close sequence, you increment the second, the 0. That's the number of opens and closes. So you increment that to 1, then to 2. And then as soon as the next bucket has k, your beam size actions in it, you drop the previous ones and you move on. Yeah. They also added a fast tracking where they found this alone was not enough to overcome, especially in uncertain cases, the desire to simply close everything and then shift. So they found it helps to simply fast track shifts to the next bucket. So you do after an action, you just arbitrarily pass a certain number of the top shifts to the next bucket, and then you continue with the previous algorithm. And they found this out. Another common problem in beam search is oftentimes your beams are going to be fairly similar. So for example, you might have a dog, the dog, his dog. And while it is sort of nice to be able to play around with very small changes, if you know you have a good translation, oftentimes you want a more diverse beam search, a more diverse beam. So you're seeing more possible actions and more possible words when you're deciding what the best one is. So this paper ended up doing a couple of things. The first thing they did was a sort of mutual information re-ranking, where it turns out if you have mutual information as it's like if you change this, parameterize this with a lambda controlling how strong you want these two things to be, it's pretty simple to show that this is equivalent to so while this term can be very complicated to calculate, if you look at these terms, and imagine you're doing machine translation, your P of y given x is simply the probability of the target sentence giving the source sentence. And P of x given y is simply the probability of the source sentence given a possible target sentence. So they imagined a re-ranking system where you train two models. You train a source to target model and a target to source model. And then when you're actually decoding, you take your target model and you generate a k-best list. And from that k-best list, you calculate the probability of using your separate target to source model of getting the original sentence from that. And then you simply add those together. And because of this, that's a rough approximation of mutual information. So they took this, and then they also had a trick, which they used to punish ranked siblings. So if you look at this example, for he is and he has, is the first best translation of he is, and has is the second best one. And it is and it has is the first best, and has is the second best. So they add a term to the beam search, which is simply a parameter, lambda or something, times k, where you're the k-best child of any particular beam. So they combined that with mutual information re-ranking to try to improve diversity in the beam, where they wanted to have high information between the source sentence and the target sentence, while still forcing the beam search to consider more than just the top k best choices of their most likely translation. And they found this improved their accuracy because it improved diversity in the beam. Another one to do, you probably don't want to do this in machine translation, but you can just sample from your softmax. I'll be talking about more clever ways of doing this later, but if you're doing conversation, if you're doing dialogue generation, there oftentimes is a lot of possible things someone can say. So if you're translating the dog into a different language, there's probably only a handful of words you can translate that into. So the distributions can be pretty peaky. But if you're just generating language in a conversation, there's a lot more things you can say. So the distribution is going to be spread out over those possible things. And that means that if you simply sample, you're more likely to have reasonable outputs than if you sample from a machine translation system, where you either get gritty results from the sampling or sort of you hit a low probability word and things kind of just fall apart. This is a really cool paper where they found a trick to do sampling without replacement, without having to do multiple samples. And this is using a trick called the Gumbel max trick, where the Gumbel is a specific distribution where I kind of use notation in writing that. The Gumbel distribution is something like e to the negative e to the lambda plus x. And Gumbel distributions are oftentimes used in predicting low probability events. So if you have a Gaussian distribution and you're trying to predict, for example, 100-year floods, so very rare, very bad flood events, hydrologists found the Gaussian distribution was underrepresenting tail end events. and they found the Gumbel distribution happened to be better than that. But in our particular case, that's a bit less important. Then the Gumbel distribution has a couple of very nice properties. So one of the properties is that if you take the inverse of the cumulative distribution of a Gumbel distribution, and you use as your random variable a uniform distribution, that is also Gumbel distributed, where the parameter theta there is this parameter here. So this means if you want to add Gumbel noise to a variable, so let's say you have a variable xi, and you want to add Gumbel noise to it, you can simply subtract log minus log of a uniform variable. So that's both easy to calculate, and it means if you add these Gumbels together, you get another Gumbel shifted by theta I plus theta x, which is a nice property to have. The other thing that just happens to be true is if you have a Gumbel distribution, the argmax of the Gumbel distribution happens to be a categorical variable. So if you give the Gumbel distribution, okay. So if you take a variable and you distort it with Gumbel noise, and you do this across a sequence of input categorical variables, and then you take the top one of those, that is equivalent to sampling by taking the max. That was a bad explanation. I guess there's two properties here that matter, and the basic idea is you take your variable list, your input variable list, x1, x2, x3, x4, etc., and you apply random Gumbel noise to those, and then you take the top k of those. That ends up being equivalent to sampling k samples without replacement from that distribution. And that happens to be the case because of this. I put a proof of this in the reading. Unfortunately, the proof, while very mechanically good, gives no intuition into why it's true. It seems to be the Gumbel just has the property that the probability of the ith variable being the argmax happens to be equal to the softmax of all of the input variables you're taking the argmax over. And because that is true, you can perturb each of your elements by the Gumbel and take the k softmax. Does that kind of make sense? So you can use this trick to do a couple of very nice things during beam search. One thing during beam search is if you want to get k unique samples without replacement, and you're just sampling randomly, if you have a very peaky distribution, as in translation, if you want k unique samples, oftentimes you'll have to do many samples to not get the top 2 or 3 words. And if you do this, you only have to perturb each variable in your output once and take the top k, and that is a k random sample. And the other nice thing is if you're trying to do instead of just taking the max during your beam search, if you're sampling during your beam search, you can run into a tricky problem where if you look at this tree, for example, and if you're sampling during beam search and you happen to pick one very low probability event, and you're at the bottom layer, let's say you pick this event by random with a 15% probability, and you also pick this event at random with a 25% probability, and you want to take the next sample, what you would have to do is essentially create one distribution from the softmax of the next output from here and sample from that. But the problem with that is this was already very unlikely. It has a 5% chance of happening. And that means the next probability is also going to be even more unlikely. So to continue down this tree, you're going to have to pick a 5% chance at random event multiple times versus just picking this 20% event multiple times. And that means by the time you're done sampling at the end of your tree, this model is going to drastically underrepresent the probability of unlikely events. What you want instead is a way of saying, we picked this 0.05 score, this 5% probability event once, and we want to stick with it. We want to say, okay, this was unlikely, but we're here already. So ignore the fact that this is unlikely and continue searching from this point without throwing it out because this is unlikely. And this Gumbel softmax tricks kind of does both. So what you do is, if you look at the graph here, the bars next to each node is their total score. And the upper bar is the Gumbel score, and the lower bar is the probability score. And you notice the probability score pretty much always goes down as you go down the tree, because that's sort of multiple, yeah, that's the probability combined of each event in the tree. So any particular sequence gets more and more unlikely as you go. And then at each step, you take your softmax, you perturb it by the Gumbel probability, and you take the top k events. And instead of using the overall probability score, you use the Gumbel perturbed probability score as the score, and you continue decoding. And because you're using the Gumbel perturbed probability score, for example, in this event, you picked a 0.1 probability event. But when you do the next sample, because you factor in the Gumbel score, the Gumbel perturbation that value got in the k top max, for your next step, it is not 0.1% chance unlikely. It's 0.1 plus whatever the Gumbel score is. And to get it into the top k max, the Gumbel score is going to be decently high. So that means you're not just going to throw out low probability events you picked earlier when you continue to sample. So at each step, you perturb the softmax by a Gumbel variable, and you just take the top k best. You do that again and again and again, and you sort of do a very nice sampling without replacement beam search, and all you're doing is making one very simple perturbation at each level, and you can sample without replacement. I thought this paper was really cool. It was one of my favorite papers that I've read, but unfortunately the parts on the Gumbel max trick were they were spread out over several papers, and none of them really gave an intuition as to why it worked. It was just, if you take this probability distribution and you calculate the max, it magically happens to be the softmax, therefore this trick works. So, yeah. Cool paper. I wish I had more intuition as to why it works, though.
Another thing about that, here is that you can see why pruning might be a generally bad thing, right? So you can see how at the bottom left, the second option has the same probability weight, like 0.15, just as the one next to it. But because of, if we did pruning, basically only keeping the ones that are dark gray, then basically you would have missed that option.
Good point. In this case, they missed that option, but that was partially because they were sampling with web noise. Yeah. And I guess another thing to mention is, although
I'm not really sure about what do you mean by sampling without replacement?
so it means if you have it means you're taking k samples, but none of the k samples can be the same. So if your vocab was man, woman, dog, cat, and you wanted 2 samples, the 2 samples can't be man, man. They would have to be man, woman, or man, cat, something like that. Does that make sense? Any other questions? Feel free to jump in if you do. Cool. So while the math behind the Gumbel trick's a little complicated, actually implementing it is pretty easy. You just generate a normal variables equal to your softmax size. You take the negative log of those, and you subtract that from all your variables, and you take the top k. So that's pretty simple to do, and you can get a nice top k sampling without replacement just from doing that. So this paper actually isn't a neural paper, and well, another way of searching is you can use more complicated search algorithms like Monte-Carlo tree search. So how many people know what Monte-Carlo tree search is? A few people. I'll go over it then. So the basic idea of Monte-Carlo tree search is you do repeated rollouts to a final state, and you use the values of those final states to update your intermediate rewards. And this is very often used in game playing, where you know what your final state is. So if you play a game of chess, even if you play completely randomly to the end state, you know who won and you know who lost. And this has been used quite a bit less in language because when I roll out a translation to the end state, how well that translation is, especially if I don't have a target, is sort of, I don't really know how good that is. So in gameplay, what you would do is you would have your initial node, like this is the current game state, and you would have several possible moves that already have been partially explored. I'll go into that in a bit later. And then you choose one of these nodes, and you run a rollout to the end of the game from that node. So let's say you choose this node, which is to move, I don't know, a pawn to a certain position. You take that move, and then you make a rollout to the end game. And you see whether you win or you lose. So a win is worth 1 point, and a loss is worth 0 points. And you roll this value back to this node, and every node behind it. And you keep track of the cumulative numbers of wins and losses at each state. So if we made a rollout from here, and we found that we lost, we would add a loss to each of these intermediate states. So for each state that you have seen before and made a rollout to the end, you keep track of a cumulative number of times you've been there, and then the number of times you've won, and the number of times that you lost. So when you search, when you choose the next state to roll out, it's a combination. You can see the equation with UCB1 there, where BI is the winning ratio. That's how many times you've won to how many times you've lost. And then the next term is an exploration term. How many times have I explored this state? So even if you have a state that looks really good, that you win all the time, if you've been there a lot already, there's not much of a point to keep going back there, because you already have a fairly good idea about how good the state is. So this is sort of a balance between exploration and exploitation, where you want to explore new states, but you also want to exploit states that you've been in before that are good states to be in. Does that make sense with what we're doing? So then we would, for example, take this move, eliminate this tree, and then continue doing the same thing from here. So there are a couple of challenges of bringing this to natural language processing. The first one is, I guess, what's your model going to be? In this case, they used a very simple probabilistic context-free grammar model. So they took a CFG, and they used that to predict the probabilities of the next moves, which in this case is which word you're generating. And then the next question is what is the end state? When you roll out to your complete sentence, how do you judge whether it's good or bad? So here they did 2 things. One of the things they did was a language model. They actually did a language model in 2 ways, so I guess they did 3 things. For the language model, they took the trigram complexity score, which is in grams. And they also took an acceptability score, which was the trigram probability score divided by the probability of each individual word in the sequence. And what that gives you is a rough idea of how well ordered the sequence is compared to how likely the words are. So you don't want a sequence necessarily to do well just because it has high probability words, if the high probability words are in a weird order. And then the other thing they did was they trained a model to predict whether or not the grammar of the sentence was good or bad. And to do that, they took a simple parser and had it, instead of outputting a parse, simply output a 0 or a 1, where 1 was this is good and 0 is this is bad. And they trained this on a combination of real data and fake data, where they took a generative parser to generate fake data. And they called all of that fake generative data bad, zeros, and they called all of the real data 1s. And they trained their parser to differentiate between real data and fake data. And then they applied this to the trees generated from their search. So you have your tree, you apply this discriminator to it, and it tells you whether it's a 1 or a 0. And then you take the output of all of those 3 things, and you decide whether it's a win or a loss. They did something like, if the parser says it's good, it's good. And then if the language model says it's good, it's only good if the parser is good, or something like that. I don't remember the exact details. But if you want to do something fancier than beam search, this is a pretty cool approach. And it seemed to work pretty well for language generation in their case. So far we have only seen search in decoding time. So you have your trained model, and you just throw search on top of this. This is fairly nice in that it makes search, especially most of these, fairly easy to add. So you have your trained model, you just throw beam search onto the end, and you get better results. But oftentimes, not oftentimes, every once in a while maybe, you wanted to have your model see what it will see in beam search during training time. So in all these previous examples, your decoding model is sort of diverging from your training. You're seeing a bunch of sentences you were not expecting to see during training. And so for some of them, like the mutual information one, you sort of kind of can get around that with trying to improve the diversity into your beam search during training time. But it might be beneficial to incorporate search into your training, so your training and decoding looks the same, and that your model knows what it's going to be looking at decoding time. The first way of doing this was they did a beam search optimization, and they trained this with something that looks fairly similar to lasso. How many people know what lasso is? A decent number of people, cool. I'll sort of go over it though, because that wasn't everyone. So let's say you have a beam of size 3. What you do during training time is instead of generating one word, I guess you would generate several possible words. And say you take the top 3 words, and you do this at each time step. Then to get a loss function, what you would do is you also have your gold sequence, and you ask, is your gold sequence in these top 3 words? And if your gold sequence is in these top 3 words, you don't penalize your model. Your model effectively got it right, and you'll probably get the right answer during decoding time. But if your gold answer drops out of these 3, then you have a loss. And what your loss function ends up being is something like the probability of the gold sequence minus the probability of each of the sequences in your top 3 choices. So that's just sort of telling your model, I want the gold probability to be higher, and then I want the probability of these sequences that you thought were better than the gold probability to be lower. And you do this down the sentence. They also have a little recovery thing, where if the gold falls out of the top 3, it's fairly unlikely to be in the top 3 during the next state, and you don't want to repeatedly punish it for making one mistake early in the training. So what they do instead is, if the gold probability falls out of the top 3, they force it back in. So these next 3 states in this example all come from a red dog runs. They throw out everything before that and continue training. So this is a fairly simple way of incorporating beam search during training, and they got pretty good results. Another way of incorporating beam search during training is simply to make everything continuous. You try to make your arg k max, like your top k arg max, continuous. You try to make the beam search continuous, and you can simply do backpropagation over all of that. So the way that they made beam search continuous was by modifying softmax. So softmax is going to return the probability of each value. But what you want it to return instead is the probability of the index of that value. So what they did was they had what's called a PT softmax, which was the normal softmax. So E of X over. But then they simply multiplied this by the index. So this is going to give you something that would look like where this is equal to the probability times the index. So this is sort of a way of doing an approximation of an argmax for one variable, where it's returning the index instead of the probability. They might have done value instead of index. So it's returning the value. I think that's what they did. So it's returning the value of index I instead of the probability of index I. And then you can, during training, simply integrate this into the rest of your thing. So this chart in particular is the hidden states in the recurrent element. So what you do in your recurrent element was you take the continuous top k argmax, and for one of those, you just sort of pass it on. That's your top k values. And then you want to upgrade the hidden state. So you sum all of those together, you multiply it by an embedding, you do a linear combination, and that's how you update the hidden state. Does that kind of make sense? Cool. Another sort of entirely different class of algorithms you can use is A-star algorithms. And I think the creator of A-star actually died recently, which is kind of sad, but I guess not kind of sad. So for A-star search, what you're going to do is you want to expand upon paths that have the cheapest cost to your target. So to do this, you need to know like what the total target cost is. So you maintain this by having a known cost to the current point and an estimated cost to the future point. More specifically, you have a heuristic. So you have g of n being the cost to the current path, and you have h of n being the estimated cost to the goal. And in A-star search, it turns out if your heuristic is admissible, that means it always underestimates the true cost to the goal, and consistent, which is basically the triangle inequality. So consistent means if you're going to an intermediate point, the heuristic to an intermediate point should be less than the cost to the intermediate point plus the heuristic to the intermediate point. So sort of a triangle inequality there. And if it's both of these two things, you can do a search that gets you to your target with very nice optimality guarantees in terms of the fewest number of paths you have to cover.
Have you guys seen A-star search before? Yeah.
Yeah. Cool. So I'm just focusing on, so a lot of these papers are basically doing A-star search, and then they're doing various fancy things to try to get heuristics that are both admissible and maybe consistent. So in classical A-star parsing, this is non-neural. They're using a probabilistic context-free grammar. And they maintain inside scores and outside scores. So they're building up constituents. And the inside score is the cost of that node down. So if you had a node that was like NP equals to dex, the inside score is the probability of this node. And the outside score is the probability of attaching this node to the rest of the tree. So you would have S goes to NP, VP say. And the outside node would be this probability. And it turns out, because this is a PCFG, each step upwards is a multiplication of probabilities. So that sort of necessarily has to be both admissible and consistent. It's going to follow triangle inequalities in terms of estimating the total overall cost, and it's going to underestimate the cost of implementing the rest of the tree because you don't know what the cost of building out this VP is. But this is sort of traditional parsing, and this was very easy to do because a PCFG gives us discrete probabilities for each action. So the question of how to integrate this into neural networks is a little bit more complicated. Here they're doing CCG parsing, which is something construction grammar is. How many people have seen CCG grammars before? Not that many. So CCG grammars is sort of a slash grammar, where if you look at the example sentence at the very top, I saw squirrels with nuts. You notice that instead of having a simple tag, for example, saw has S/NP/NP. So these are called super tags. And how CCG grammars work is you concatenate, the slashes means it's missing this. And you concatenate with that element to the right or left. So for this example, I saw squirrels with nuts. You have width with and you have nuts here. So this slash NP means it's missing an NP to the right of it. So your tree is made up by a bunch of, I guess, unification of these rules, where you say, this is missing an NP, there's an NP here. So this constituent is now an NP slash NP. Yeah. And then you have squirrels here, which is an NP. So you can say, there's an NP missing here, there's an NP here. So I can unify those. And you sort of continue down the tree. Does that make sense? So CCG parsing, in this case, they were focusing on the tagging. So if you can get a good tag to your top constituents, you can sort of do these rule-based approaches on how to unify them all. But this is a slightly, or maybe a much harder task than traditional part-of-speech tagging, because there's a lot more potential tags. So with, instead of being a PP, is this constituent that's saying, I'm missing an NP here, and I'm missing an NP here, and when I'm completed, I'm going to be an NP. So their task was essentially a harder part of speech solving task. So they tried to use an A*-ish approach in solving it. And how they did this was, they said, the inside score, the cost to the current point, is going to be the score enclosed in this band. So here would be this band. You simply sum each word with the probability of having the tags you assign to each word. And the outside span, you do the same thing for every other word in the sentence. So at that current point, what is your tag for each of those words? And that's your outside score. That seems to work pretty well, but is this admissible? No. They sort of did an A*-esque thing. So you can make this heuristic admissible, potentially, by what this Lee et al. Paper did was they were doing something fairly similar, except for the global model is they trained a tree LSTM over the entire parse, and then they took this and they subtracted that from each of the estimated outside scores. So that meant that the estimated outside scores are going to be less than 0, which means they're sort of trivially admissible. And because calculating a tree LSTM over an entire sequence is fairly complicated, they did this sort of lazy thing where they first evaluated the score, and then they expanded only good scores first. So instead of trying to search over like all the potential scores, they sorted the order of scores to sort in. One thing I didn't get out of this paper was whether this was consistent or not. They got better results than the other papers, so presumably making it admissible makes it better. But if this has A* guarantees, I'm not entirely sure. Another potential thing to do is you can estimate future costs. So we already kind of saw this with some of the pruning stuff or Monte-Carlo tree search stuff, but here they did this very explicitly. So let's say you're doing machine translation and you have a weird situation where you want to be able to control the output length. Alternatively, this can also be used as a way to sort of train directly against blue score. And they did this by doing a sort of actor-critic thing, where the critic was trained entirely independently of the actor. So in this case, the actor is just going to be an LSTM, basically. It's just going to be an encoder. And then they train a critic, which takes the hidden states of the encoder and predicts the values you want. So it'll take the hidden state of the encoder and predict blue score. And then during training time, you simply take the output of your encoder, and then you take the prediction of the blue score, and you combine those. I think they did a linear combination with controlled parameters, and they used that to decode. But while their control over blue score was okay, I guess, I really liked what they did for length. So what they did for length is at each state, instead of predicting the total length of the sentence, they predicted the length of how many variables are remaining. So you take a hidden state, you predict that the length of the first word is the length of the sentence, then the length of the sentence minus 1, and length of the sentence minus 2, etc. And then they can concatenated those embeddings during decoding time. So what you could do during actual, like your test time, is let's say I wanted an output sentence of length 5. You could tell it, I want an output sentence of length 5. And then you are going to initialize the first n equals 2 to 5, and essentially run the same thing, where you're forcing the soothsayer network, your critic network, the same way you force during training time with chosen lengths. And they found this was a pretty good way of controlling lengths without arbitrarily cutting the decoder off after a short time. I think, I'm gonna skip this. I think this paper did a similar actor critic thing. They didn't look at length specifically, but I kind of liked what they did in terms of training against blue score a little bit more. So they did the same thing for machine translation. You have, and this is sort of borrowing from reinforcement learning a bit too. So you have an actor which predicts the next action. In this case, the next action is the next word. You have a critic saying, I'm going to predicting the next word is going to have a certain blue score. And then they trained this action and critic. They trained the actor similarly to reinforce. We'll see exactly how in the next slide. They found with a critic that if you simply train over random generated sequences at the beginning of training, sort of similar to reinforce, you're going to have a lot of garbage sequences. So it's going to be really hard for the actor to learn much more than all of these sequences have a blue score of 0. So they trained this with temporal difference instead. So for the actor, they trained this over set of examples, the possible sequences, and the number of actors there. And they modified the backpropagation term. And then the reason I showed this here is you might notice that, I don't know how many of you remember what exactly reinforced looks like, but what reinforced did was they had the same probability over theta, and this is just your normal backpropagation term, and then they modified this by your predicted reward minus your average reward. So here, instead of doing a simple predicted reward, they have a more complicated critic function that they're replacing that with over the entire set of possible actions. Does that kind of make sense? So it's kind of reinforcey with just a little bit swapped out. And then for the critic, they trained this as the actual reward minus the predicted reward squared, so just like a normal regression function. But then they also had the CT term here is an average reward over all of the possible other states. So it's saying that you want your reward to be high, but you also want your reward to be higher than the average sequence reward. And they found this got pretty good results. Anyways, that's actor critic. Cool. So back to A-star search. A-star search gives you very nice optimality guarantees, and it has strong results in CCG parsing. But unlike, say, beam search, where you can take any model and just sort of slap it on at the end, and you're probably going to get better results, here you need to do a bit more engineering. You need to figure out how to have an admissible, consistent heuristic. And so because of this, it tends to be used a lot less, except for in places like CCG parsing, where it's already being used in nominal balls. There's a couple of other search algorithms I wanted to go over to. This one is a particle filter. And you can think of a particle filter as a variable size beam search, where the beam size is controlled by the confidence the model has in each of the predictions. So, for example, let's say you're running a particle filter with 100 particles. At each time step, you're going to redistribute those 100 particles equal to the probability of each choice in your beam and prune everything that doesn't have a particle. Then you're going to do this again and reproportion the 100 particles. So this is a pretty simple, I guess, addition to beam search, where instead of, say, having a beam size 15, and then having 7 of those examples have really low probability, you don't even want to expand those really low probability ones each time. You just throw them away, and you assign all of the particles to the more higher probability ones. So they did, this was also generative parsing, so they had the same problem with shift, where shift has a lot of possible actions equal to the size of your vocab. So they did the same thing where they compared after equal numbers of shifts and not after equal numbers of actions. But the big thing here was just the particle filter. And another potential thing you can do is re-ranking. So this was done classically in machine translation, a lot of the time with a language model. So you have your translation model, and you have it produce a bunch of possible outputs in the target language. And then your translation model. And then you have your language model, and you use your language model to score all of those possible translations. And you re-rank based on the language model score. And you can kind of do something similar here with systems, but instead of doing a translation model and a language model, in this paper they were doing something similar to the constituency-based parsing, where they had a bunch of opens and a bunch of closes. So searching with they also made both a generative model and a discriminative model for this. And searching over the generative model was hard because of the same shift problem, where you have a million possible opens and you have a million possible shifts. So what the model tended to do was make an open and make as many possible closes as possible. So what they did instead was they trained a separate generative model and a separate discriminative model. Then they parsed with the discriminative model, re-ranked with the generative model, and they found they got good results. They also tried it the opposite way, but because of the previously mentioned problem, they got worse results. So they ended up using the discriminative model first, and then re-ranking with the generative model. So if you have two similar models, you can use them in this fashion, where you're using one to re-rank in your search. Yeah. Any questions?
Is the particle filter algorithm just a beam search with a threshold on the probability?
You can think of it. I think it's like that, except for instead of specifying a threshold, you're sort of specifying how you want your. So if you have a particle size of
So you just throw in, say, other branches that have less than one particle size.
Right, so
and say the number of the vocabulary, say you're doing the sequence generation and your number of vocabulary is fixed. And it's pretty much like saying that, okay, whatever the probability assigned to that is lower than 1 over the vocabulary size that you select.
right.
It's like a threshold.
Seems to me threshold is like an acquisition variation rather than a So it depends on the variance. If things are more coherent, then you have variance.
I guess it is equivalent to the threshold I showed earlier was like a threshold around the best scoring one. And in this case, you're doing simply an overall probability threshold. So instead of saying throw out everything that's not within 50% of the best score, you throw out everything that's under 1% or whatever. Any other questions?
And tuning the threshold is not an easy thing, right? It can be a function of like your output vocabulary or how far in you're into generating, for example. So this, the option of using the model's intrinsic uncertainty seems much better because it doesn't necessarily need to be tuned in the same ways.
Good point. Anything else? Thanks.
Okay. Well,